Hello, I'm Haran Raajesh and I present our work MICap, a unified model for identity-aware movie descriptions, now with Naveen, Reddy, Zeeshan and Makarand Tapaswi. In this work, we focus on identity-aware captioning, emphasizing understanding the identities of characters across video clips rather than merely describing the actions taking place. Prior works in video captioning have largely ignored identities, replacing character names with someone tokens. However, recent work like MVAD names, MAD, and LSMDC with names have begun to shift the community's focus towards identity-aware captions. While MAD and MVAD names provide the names of the movie characters in the ground truth, LSMDC takes a different approach. LSMDC instead provides local IDs to characters within a video set consisting of 5 consecutive scenes from a movie and formulates 2 identity-aware tasks. Given the videos and the captions with someone blanked out, the first task is to fill in these blanks with the correct IDs. The other task requires generating the full caption given the video set. We propose MICap to tackle this problem. We extract 2 types of features, text and visual features. For the text features, we get BERT features for the blank tokens concatenated with the CLS token. These features are used only for the fill in the blank task as they assume access to the captions. For the visual features, we extract 3 different types of features. I3D features, pre-trained on the Kinetics 400 dataset for action representations. Arc face features for face representations. And clip features for overall scene representations. Once the features are extracted, we pass them through linear layers to project them into a common embedding space. We then provide multiple embeddings for the features, each of which provide additional information. To the blank features, we add type embeddings that distinguish between different input modalities and video ID embeddings that identify which video in the video set the feature comes from. To the action features, in addition to type and video ID embeddings, segment embeddings are also added, which identify from which part of the video the feature comes. Each video is segmented evenly into 5 parts. For the face features, along with the earlier 3 embeddings, we compute clusters using dbScan and add a cluster index and bounding box embeddings. And finally, to the clip features, we add only the first 3 embeddings, type, video ID, and segment embeddings. These updated visual tokens are then passed through a transformer encoder, whose output is used as the captioning memory for the decoder. For the final step, an autoregressive decoder is used. For the fill-in task, the decoder takes all 4 modalities in its memory and generates only the person ID labels. The remaining tokens are taken from the ground truth as they are given in the fill-in task. For the full captioning task, the decoder takes only 3 modalities in its memory as text is not available and generates every token in an autoregressive manner. As both tasks use an autoregressive decoder, the parameters can be shared between the decoder for both tasks, allowing for joint training objective. Now we shift focus to identity-aware metrics. Current captioning metrics like Cider and Blue do not emphasize the correctness of identities in the caption, making evaluation difficult. To remedy this, we propose a new identity-aware metric, iSpice, which is built on the SPICE metric. SPICE converts both the reference and the candidate captions to scene graphs from where it obtains tuples, and goes on to calculate the F1 score over both these sets. iSpice intervenes at this stage and filters out the tuples that do not have an ID and splits the remaining into 2 groups, one with only one ID label and the other with an ID label and any other token. The F1 score over both these groups are calculated and the product is reported by iSpice. Next, we show the sensitivity of captioning metrics to ID permutation in the ground truth. We see that iSpice has the biggest drop-off across different ID permutations, showing that it is the most sensitive to mistakes and identities in the caption. Next, we show some results. MICap achieves state-of-the-art performance on both LSMDC tasks, fill in the blanks and full captioning, over previous methods. Next, we show results of the joint training method. As you can see, joint training improves performance on both tasks, training on them individually, and also we see that MICap outperforms VLMs like T5 and GPT-2, showing that integration of this identity-aware memory is not trivial. Attention analysis of MICap shows that it has a tendency to look at relevant features for different types of tokens in the caption. While generating person IDs, MICap focuses more on the face tokens as compared to the action tokens, and the opposite is true when looking at non-identity tokens. This makes a lot of sense as face features contain more ID information. Thank you for your time. All material and code from the project is available at this project page.